Good afternoon again, everyone. Go ahead and get that daily quiz up for y'all. So I'll give you all a few minutes, I guess, again, until 2:04. We'll just make it 4 minutes. But today's daily quiz, there's a lot of detail, but you don't have to look at too much to get the answer. So you remember what key parts to look for. So we have this differential equation. So the derivative of y with respect to t is equal to 4 times y plus 4. You know that solution y has to be 1 when t is equal to 0. And save you some trouble. From this, you get the solution, based on all the work that we did, is going to be -1 plus 2 times e to the 4t. So in all of this, you could solve for it again if you want to. There is an equilibrium value. So if my function y of t is constant at -1, the differential equation will never change. Is that equilibrium value stable or asymptotically stable, or is there enough information to even deduce this? Stable, unstable, or is there even enough information to deduce this? I got done writing it down. Let me share. Different screen. All right, I'm going to give you, well, I said 204, 20 seconds. But I think I've got most everyone. So I'll actually say 30 seconds, but. All right, gonna log answers here in 10 seconds. I think I got everyone in though. Maybe just missing one. Locking answers in 5, 4, 3, 2, 1. Locking answers now. So we are, I think that's, oh yeah, we had someone change. We're actually now at 50-50 on the split. So I gave you most of the information that we could gather based on all that we discussed, but you really don't need all of it to figure out whether or not this thing is stable or unstable. We actually came to a few conclusions based on studying a very general case. So we said, hey, let's start with just studying differential equation in this form, a number times my solution plus another number, and then just give it some initial condition. We know that the equilibrium value is always going to be at negative b over a, where b is the number I'm adding on and a is the number I'm multiplying my solution by. In this case, both of those are a positive 4. So if I take a negative 1 times the 4 divided by 4, that's where I get that equilibrium value of negative 1. But from that, and knowing the form and knowing what the solution is then going to look like, we came down to 2 cases. And whether or not that equilibrium point was stable, asymptotically stable that is, or unstable, depended upon what value, what letter. Actually, sorry, let me move it up.
The value of A.
Yeah, the value of A, right? That number that I'm multiplying the solution by. When I go back to how it was written, A times Y, A is a constant multiplied by my solution Y. And we did all this work in general to say, well, we can actually go ahead and determine if A is positive, then I know that equilibrium has to be unstable. Because this exponential part of my solution is going to be getting larger and larger and larger. So it's going to be going towards infinity. And then whether or not it goes to positive infinity or negative infinity just depends on what that coefficient is. But either way, it's going to be always going to either a positive infinity or negative infinity, which means I'm going away from that equilibrium value, making it unstable. It's only stable if A is less than 0, because then this exponential term is going towards 0 or going towards 1. And then when I combine those coefficients in the right way, it's going to end up being y naught, not negative, or negative b over a. Because it is, why do I have 0 there? I don't know why I have 0 there. That'd be e to the 0, which is 1, and then it'd be going towards y naught. Should be going to b over a though. Anyway, I know that theory is right. I can fix the tad bits of information there. But the key is that 4 is positive that I'm multiplying the y by, which just means just looking at the differential equation, I know that this equilibrium of negative 1, it is what? Because that coefficient's positive, I know my equilibrium's got to be what?
Unstable.
Unstable. Oh, I know why. That's right. That's all right. Sorry. Let me not play ping pong with your brains. Then the equilibrium we don't need to do any crazy meta-analysis because we've already done it. I can now use the results of what we built together in class. So before I go back and say that where I thought there was a mistake, it isn't a mistake, and I can explain why, I want to just try to stick us to the daily question real quick. especially for those of you who said asymptotically stable. Thumbs up if you're good, you understand it now, or what I was at least looking for. If not, please ask a question. So John, I already see you raise your hand, so go for it.
So I was looking at the solution instead of A, so negative B over A. So I looked at -1. So that's why I put asymptotically stable instead of
So, okay, but even if you consider the solution itself, you know the equilibrium is at -1, which is there in the solution, right? That's why we see the -1 plus blah, which is 2 times e to the 4t. But the only thing that's changing with respect to t or time is that e to the 4t. So I can use a couple limit laws to zoom in. And say, okay, just need to figure out what the limit of e to the 4t is going to be as t goes to infinity. And then multiply it by 2 and then add that to -1. But e to the 4 times t, what's going to be happening in that function as t gets larger and larger and larger?
It's going to get larger, it's positive.
Yeah, and it's going to be going towards positive infinity. So if I double a number that's keep getting larger, I'm only just making it a little bit faster. And then if I just add -1 to it, that's not going to be changing the fact that that number keeps getting larger and larger and larger. So as time goes on, I'm never approaching the equilibrium. In fact, I'm getting farther and farther away from it. So in that, it is an unstable equilibrium. So that's part of the reason why I did give you all the information, so you could go do an analysis like that. So the fact that that's the way your brain wanted to go about it is a 100% good way to look at it. Maybe a little bit more work, but absolutely acceptable. So there's probably just one little small mistake that occurred on there to get you to, or no, you said unstable. You didn't say asymptotically stable, never mind. But yeah, that type of analysis is absolutely correct. We just found out through looking at it in general, we don't even have to do that much work. We just have to see if a number is positive or negative, and we automatically get the result, which is part of the reason why we like to establish this theory. All right, sorry. Any other questions? All I did was an echo chamber there.
All we
So
have
any
to
other-
do was just focus on A.
Yep,
the value of A.
that's what we came up with on Friday.
Okay.
This is why we love differential equation theory, or at least people who apply these models love people who can study differential equations, because you can, and you also seem smart, right? Once you make this trick and you show a differential equation to a friend, and all you realize is I need to look at that coefficient at A, and you can already make a lot of you can already state a bunch of facts about the solution. Now it's going to act, you look really, really smart, right? So that's why people love those who can do differential equations and understand kind of some of the inner workings of it. All right. One thing, and I don't know why you should have just ignored me. This is correct. It goes to -b over a, because if this a is a negative value, like let's just say -1 to try to get a particular example, this is e to the -t, and I'm not considering, I don't know why in my head I was thinking I need to plug in t to be 0, because that's not what's happening. You're considering it in limit as t goes to infinity. So as t is getting larger and larger and larger, e to the -t or -2t, anything like that is going to 0, which is why that term gets erased and you're just left with the -b over a. So sorry for making that little bit of confusion, potentially, if anyone even picked up on it. All right, so before we get into the stuff I want to talk about today, any other questions? All right. Really wish the lady beside me wouldn't burn incense. Stuff is strong. Anyway, so in chapter 2, our goal is to find ways to solve differential equations of the following form. dy over dt is equal to f of y times t. Okay. So we have come across a very specific case of this. Whoops, I don't know why I did why comma t, usually we write it t comma y, but I guess it doesn't really matter. So far we have only worked with things of the form f of t comma y is equal to a times y plus b. So very specific instance. It's only acting like a line where the variable is the solution of the differential equation we're looking for. Okay, and we don't want it to be just like that because that's probably not going to be what all differential equations look like. In fact, there are many, many different forms. There's many, many different ways to combine your independent variable t as well as your solution, right? We could do f of t comma y is equal to something like this, my solution squared plus my independent variable times my solution plus 3. Or natural log of my solution minus 1. Or I don't know, just to get one more because rule of 3 is awesome. E to the t plus y minus 4, right? As of now, we haven't, at least in this course, established ways to go about solving any differential equation like this. We might be able to follow a similar trick that we did before, you know, trying to get a form that when I integrate it nicely, it's going to turn into a natural log. That might not work. I might have to do integration by parts, various other things. So we're going to have to kind of pick a class of functions to work with. And the best thing to do in anything that you do in theory for mathematics is just take small steps from what you currently know, make adjustments to it, and then see how your established theory can expand, right? I don't want to go straight from learning about physics or learning about, or yeah, I'll just start with physics example. You know, you're in your 241, physics 241, and then immediately start talking about quantum physics and black holes. Right? You don't want to make a crazy jump in theory like that. You make small steps, make small observations, and keep generalizing, generalizing, generalizing until you can get to that point. So we're going to start off with a form of equation that's similar to this linear one, right? This a times my solution y plus b. But we're going to make a couple assumptions in that. One, those constants, that a and b, don't have to be constants. They can be functions of your independent variable t. So we're still looking at something with a similar form. However, it's going to allow us to see another little integration technique that we're going to get to use to solve these. So I have some function q of t, which is going to be with respect to time. So it's some combination of my independent variable t. Okay, I'm multiplying it by my derivative dy dt. Then I'm adding that to another function of time, t. It can be different, same, whatever, of q of t, times my solution. Then it's all equal to some combination of my independent variable t. So we're going to actually be able to solve this. It's just a small little difference from what we did before, because if I've moved that p of t times y over and then divide by q of t, and this is, of course, assuming this function q of t is non-zero. It would make sense to begin with, because then my derivative would be gone. That dy over dt term would be gone if it was zero. But this is still something of that form. Dy over dt is equal to f of t comma y. It's some combination of my independent variable t and my solution y. So it's still within this class of equations. We're just writing it differently because the way we write it is going to also help unlock the way we go about solving. Now, without having a ton of experience and being extremely confident with a lot of your Calc 1 and Calc 2 skills, it's going to be a little hard to actually see where the solution for this comes from, that really the trick to solve these types of differential equations comes from. So we're going to try to just start with a specific example. And then once we recognize a specific example, see if we can then use that to then work on a way to solve this more general form. We're going to do a motivating example. I want to solve the following. Sine of t times the derivative of y with respect to t plus cosine of t times y is equal to 4 times t squared. So I want to solve this, which means I want to get rid of something. Now you're going to stare at this equation for a long, long, long time. And I have to start thinking about, okay, my goal is to integrate. I need to integrate to get rid of a derivative, right? So I'm going to want to integrate something that is nice to do, that already has a derivative. Now, first thought based off of that might be, okay, move the cosine of ty term over, so then I only have my derivative on the left-hand side, and then try to integrate that. But then it gets messy because I'm multiplying by that sine of t. And then on the right-hand side, I could integrate 4t squared, but then what is the integral, the antiderivative of cosine of t times y? Because I don't know why. That's what I'm trying to figure out. So, okay, I start racking my brain and go, well, as long as I know if this is the outcome of a nice derivative, and I take the antiderivative of that outcome, then I can take it back to what was originally there. So I'm going to start viewing one side of this equation as the outcome of a derivative. So then I start making some observations with that in mind. Sine of t. What's its derivative with respect to t? Or the derivative of sine is what? Yeah, I think it's all, yeah, cosine. It's the derivative of cosine. Well, then also look here. I have the derivative of y, but then y. So when I think about what I see on that left-hand side right there, I have a function times one derivative So I have sine times the derivative of y, but then I'm multiplying that by the derivative of sine times y. So this is sine of t times the derivative of y with respect to t plus y times the derivative of sine. And there's a very, very important calculus derivative rule that has an outcome that looks like this. Anyone remember what the name of the rule is? Derivative of the first times the second plus the derivative of the second times the first. Sorry, I interrupt you. What was that, Raquelia or Kyla?
Michaela, product rule.
Okay. Yeah, product rule. And thank you again for the correction. I'm slowly getting, I try to correct myself, but it's a little too late. But yes, I'm going to be viewing this as the outcome of product rule, which means that this is the derivative of sine of t times y. Well, hey, it's not a simple looking function necessarily, but I'm looking at the derivative with respect to time of a function and then equal to, on the right-hand side, a function that I know I can integrate. 4t squared, I can definitely integrate. So now let's do that. Cancel out the derivative on the left-hand side, integrate the one function that I know, which is that 4t squared. And now I have unlocked how to get to that y to figure out what it needs to be. So on the left-hand side, what is that derivative going to be? Or antiderivative going to be? I apologize. On the left-hand side, antiderivative of a derivative. What happens to those two things? Yeah, they cancel each other out, leaving you with just what?
The sine t.
Times what?
Oh, yeah, y.
Yeah, sine of t times y. And then all I need to do is figure out, okay, what's the antiderivative of 4t squared? What is that going to be?
Four t cubed over 3.
Yep. I'm going to write that as 4/3 t cubed, and then I've integrated on both sides, which means I need to include what?
A constant c.
Yeah. The integrating constant c. Again, I technically get one on both sides because I integrated on both sides, but I can combine them together into one total constant, which I just then referred to as c. Now I'm really close. What's y? Or what do I need to do to find out what y is? Yeah, I see it. No, you're good. I saw you mouth it. Divide by sine. Yeah. So this is 4/3 t cubed plus c, all divided by sine of t. And then there's just this important assumption that we have to make. This only works as long as sine of t is not 0, which is a nice simple assumption to make, because if I go back up to my original problem, if sine of t was 0, then I'm eliminating the derivative there, and I've got nothing to solve for. So we already have that standing assumption that for this to be a differential equation, I need a derivative somewhere in the equation. So sine of t should not be permitted to be 0 to begin with. Okay. So from making these clever observations, what's happening, the main thing is if I look at this combination of my derivative and my solution, So I move them to the same side. I look at something times my derivative plus something times my solution. I want to see if I can make that always look like the outcome of the product rule. Because if it's the outcome of the product rule, I know what the two parts are. One's going to be y and one's going to be whatever that function is that I'm multiplying by. And then it's going to be easy to integrate that and get rid of that derivative so then I can start figuring out what y needs to be. So now let's try to take this idea back to that general form. But before I do that, I should pause. Thumbs up if you're following along and feeling good, but this is a perfect time for any questions you may have for me. All right, okay. I'm guessing people are writing down. Just a slow slew of thumbs up, but I got them all for the most part. So like I said, let's try this idea for the general version. Because now we potentially have a way to tackle that. So we go back to Q of t times my derivative plus P of t times my solution is equal to some function G of t. But what do I need to know? If I try to apply that same idea, I have y and its derivative, but what was the necessary connection that we had before that I don't necessarily know right now? So before this Q of t was sine of t, and the P of t was cosine of t. What was the relationship between sine and cosine that was necessary?
Derivative.
The derivative, right? Do I know? And I'm trying to keep this very, very general, right? Because I don't want to solve just a particular case like we did above. I want to solve it for any potential case. Do I know? Oops, I'm hitting a dead zone on my screen, sorry. Do we know that the derivative of that function q is equal to P of t? Have I even defined either of those functions for you?
Are you talking about only in this circumstance?
Yeah, well, in any circumstance, technically, because I'm keeping it super general. If you want to think of this general situation as a particular circumstance, then the answer to your question would be yes, which is probably not helping you out too much. But if I never tell you what Q is and what P is, can you guarantee that the derivative of Q is P? No. And you can come up with different examples where that won't be true. Right? I could do a sine. I could go back to that first one and do sine of t times my derivative plus natural log of t times y equals, I don't know, 3t squared again. Derivative of sine is definitely not natural log of t. The question is, though, is that still going to stop this idea from happening? Answer is no. I'm just going to have to be creative. So just to write this all out, we are not guaranteed the derivative of whatever that function q is, i.e. the function I'm multiplying my derivative by, the dy over dt. You're never going to be able to, in general, assume that it is. And even if we just said, okay, well, let's make this assumption so things will work out, you're then limiting the different types of differential equations that this form can be. I never want to assume that the derivative of Q is P. But we can still solve this. But we can still solve this by making it work. And I'm putting work in a quotations here, because I'll never be able to change what the derivative of Q of T is. But I can change the derivative of the function that I'm considering and hoping that it matches up with when I also change Q and I change P by the same thing, that then this new function that I create is going to work out. This idea of making it work is we're going to multiply my entire equation by something called an integrating factor. It's an integrating factor. The factor is coming from, we're going to end up using it to multiply my entire equation. And then integrating is we're going to choose it in such a way that it allows me to look at that left-hand side of this differential equation as the outcome of a product rule. And then I can use that same technique, say, okay, then this is derivative of a function. And then I can integrate that derivative really quickly to get rid of the derivative and then solve for y. So I'm going to zoom in for a moment, just a little bit. That integrating factor, it's supposed to be a comma here, is going to have a special symbol because it has a special purpose for us. It's going to be the Greek letter mu, mu. It kind of looks like an M. The way I like to describe how to draw it, if you're not used to it, is just do your standard Arabic U, and then create this really, really long tail coming off the left-hand side. It's a pretty good way to write the Greek letter mu. It's not perfect, but it does work, okay? So we're always going to use that symbol mu to represent that integrating factor. This will always be done so that we can undo the product rule that we spotted before. So again, general with this new idea might be hard to nail down, right? So take an example, take a specific example, work with this concept and make sure you can kind of flesh out the details of the idea. Then once you have it working in a particular case, see if it's easy to take that same logic and then just expand it to any other case. So we're going to consider a basic example. We're going to make this differential equation have some nice, easy functions to use so that I don't have to worry about too much. When I mean make it simple, I mean make it simple. Make the function q just be the constant function 1. Let the function p be the constant function -3. And then g of t just be t. Right? I don't want to have to do anything crazy. So then what I want to do is multiply everything in this equation by that integrating factor mu. I don't know what it is. I'm just saying, okay, there should be something I can, let's say it exists, multiply, and then see if I can flesh out the details a little bit later on. So if I multiply everything by this integrating factor, mu of t, this is going to be the derivative of y times mu minus 3 times the derivative of mu of t, or not derivative of mu of t, just mu of t, I apologize, times y is equal to t times this integrating factor mu. So now, for this to be the product rule, I got the derivative of y and y, but then I need to have my function u, and I need its derivative to be -3 times mu. So for the product rule idea to work, I said, wow, combine product and rule into one word. So what we need is the derivative of this integrating factor to be -3 times the function. So really just a constant multiple of itself. Well, I have to start thinking through all the functions that I know. Of those functions, you have polynomials, you have log functions, exponential functions, trig functions. Those are big classes that you always study. Which one of those types of functions can I take the derivative of it and I see the original function appear in the derivative, at least in some form? What function can I take the derivative of, and its derivative is itself?
E of t.
Yeah, e of t. Derivative of e to the t is e to the t. And then there's this little rule that comes from that, thanks to the chain rule. If a is constant and I consider e to the at, its derivative is going to be what? Again, where this calculus gets to come back and haunt you. So chain rule, I take the derivative of the outer function, which is that exponential function. Derivative of, oh, go for it. Yes, please.
E of a of t times a.
Yeah. So you take the derivative of the outer function, which is that exponential e to the x, derivative e to the x, you plug back in your inner function, which is why you get the same function that you see overall, e to the at, and then multiply it by the derivative of the inner function. Well, the derivative of a constant times t is just going to be that constant, which is also can be written as a times e to the at. And more importantly, we don't have to just consider where it's a constant times my variable in that exponent. If I take the derivative with respect to t of e to any function of t, I get that its derivative is going to be the derivative of what's in the exponent times the original function, e to the ft. Well, that's going to give me a way to think of a function such that when I take its derivative, it's -3 times the original function. So for this base example, we're going to say, let my integrating factor be what? Give you a hint, it's an exponential. This is what I'm trying to make sure. When I pick mu at t, it satisfies that. And when I take its derivative, it's -3 times the original function.
Like e raised to -3t.
Yep, just e raised to -3t. If I let mu just be this, e raised to -3t, then that equation that we said before, my integrating constant times dy over dt minus 3 times my integrating constant times y is equal to t times my integrating constant. This will become e to the -3t times dy over dt minus 3 times e to the -3t, all of that times y is equal to t times e to the -3t. But we chose mu to be e to -3t because this left-hand side, I have the derivative of y, and then I have y. I have e to the -3t, and now I have the derivative of e to the -3t, which means this is the outcome from a product rule. Specifically, from taking the derivative of e to the -3t times my solution y. So we're going to have to integrate. Though we're halfway through and I need to get some water. So first thing I'm going to ask, does anyone have any questions at the moment on kind of what's happened? We're not done. We're just at a decent stopping point. Any questions so far? If not, give me a thumbs up, please. All right. So we're going to just take a quick 2-3 minute break. It's 12 or 2:48 on my time. It's about, it's just turned 2:48. So I'm going to say 2:52, everyone come back. You'll hear me start yelling at you. But if you want to, go ahead and turn your camera off, make sure you're muted so you can get up, stretch, get some water like I'm about to do. We'll come back and finish this out because remember, we're here till 3:15 on Monday and Wednesdays. Okay, but remember 2:52, which is like 3 minutes pretty much from now. All right, just to let you know, I'm back early if you have any questions for me or anything you want to talk about while we're still just on this little bit of a break. But if not, you're just listening to me, you're still good. You still have like a minute and a half.
I have a question just out of curiosity. I had seen in the announcement that the dean had say if you test positive to not come class. I wondering how would that work if you do test positive?
So after this week, what you do is you reach out to me. I haven't fully finalized the method in which I'm going to do it. I'll tell you all Friday before we have to, or pretty much at the last minute when we have to start worrying about it. But essentially, what would happen is you'd be allowed to join via Zoom that day or until you test negative again. But I'm going to be removing this current Zoom link and I'm going to be holding on to a new Zoom link privately. So I'll be, if any situation like that arises, I'll give out that Zoom link, but it's not ever going to be available in case someone, just decides that it's more convenient for them to join via Zoom versus coming to class. So it's there. There's just a barrier of entry to get on Zoom.
Okay, I was just wondering.
Yeah, no, you're all good. That's something I was thinking about as well. So, because it's not even just if you test positive. What if you are close contact, right?
Yeah, because I was seeing in the announcement that he mentioned to not come class, but he didn't like provide a plan on what to do if the event happens, you know?
Yeah, and that's in part because at the administration level, it's hard to create a generalized plan that will be easily applied to every different type of class and every different scenario for like a lab and what the instructors are comfortable, et cetera. So it's one of those things that it feels like they're kind of pushing the planning off for scenarios like that to us. Which also I kind of like because then I get to determine what happens in my class and what doesn't. But I'm never going to do anything where I'm purposefully putting people at risk.
Okay.
Mhm. All right, so it's 2:53. So everyone, come back to me. Cameras back on, please. Thank you, thank you. I got most cameras back on. When everyone's back on, but I'll satisfy for this. So we have now set up this idea of integrating constant, and then we can figure out or now integrate this form because the left-hand side I can view as the outcome of the derivative of this function. So then when I integrate a derivative, they cancel each other out. I'm left with just that function inside. So we're going to want to integrate both sides of this equation. And we're going to see another thing from calculus 2 in this case that we're going to have to remember that's very, very important. So I'm going to integrate with respect to time of both sides. And one of those integrations is pretty easy to do. Which one is it? And what is the value of that integral?
The one on the right is just gonna be t e to the minus 3t.
So the antiderivative of t times e to the negative 3t is t times e to the negative 3t.
Yeah.
So you're saying that means then that it's its own derivative. But if I took the derivative of t times e to the negative 3t, what rule would I have to apply?
Chain rule?
Chain rule will definitely be in there. So it's not a wrong answer. The first rule I have to do is product rule because I'm multiplying two functions together. So it'd be the derivative of t times e to the negative 3t plus t times the derivative of e to negative 3t, which derivative of t is 1. So this is e to negative 3t plus t times negative 3 e to the negative 3t, which is going to be equal to, even if I factor out that e to the negative 3t, a 1 minus 3t e to the negative 3t. So I then know the antiderivative of 1 minus 3 times t, all of that times e to the negative 3t is t times e to the negative 3t. But it is not its own derivative and or antiderivative. So that's
Is that-
actually not the easier of the two. Oh, go ahead, sorry.
It's okay. I was asking if that was supposed to be dy or dt, because maybe that's.
Oh, that might have messed you up. Yeah. So, oh, wow. I love that actually, because you're technically correct. And that is the best kind of correct because of my mistake. Yes, because you'd be integrating with respect to a different variable. T would be considered constant. So it would have been, I'll just write it down here real quick. Antiderivative of t, whoops, that's an e. Would be t times y times e to the negative 3t plus an integrating constant c, since the variable that I'm integrating with respect to is y in that case. So yeah, I love and hate that. It's the hate I made that mistake, but I love that you said the right answer to it. But sadly, that's not what I'm hoping for. So thank you for helping me get that corrected. And then I'm going to ask again now that it's corrected, because hopefully it's going to be a little bit easier. This is just extraneous work, so I'm going to, oh wait, I can do the mass delete. I'm going to erase it. Now that we have that fixed and I'm looking at these two integrals, which one of those two is going to be easier to probably do? Left-hand side or right-hand side of the equation?
Left hand.
Yeah, left-hand side, right? Taking the antiderivative of a derivative, they cancel each other out, just leaving me with that e to the negative 3t times y. Ooh, all right. Part of the reason why I just didn't go ahead and solve for it, just rewrote it, is because now I need to figure out what the antiderivative of t times e to the negative 3t is. It is possible to do. This is something that you do in calculus too, but it requires you to use a specific technique that you learn about. So anyone have an idea or a guess of what we should use here to figure out that integral?
I think it's substitution.
Oops, let me turn volume up. That might be my problem. Do you mind saying that one more time?
Would it be the substitution?
Can we do substitution here? What would you use as your substitution? I'm not going to say no because I just didn't think of that.
Nah, yeah, I was just guessing.
Ah, gotcha. So, I mean, it's possible if you pick the right thing to substitute in for. I don't think, well, I guess technically what I'm going to be doing is a type of substitution. I'm going to write that out, see if that jogs any memories. IBP.
integration by parts.
Yeah, integration by parts. Okay. Because what integration by parts allows us to do say, hey, if I'm looking at two things, and these are for indefinite integrals. If you remember your Calc 2 very well, there's a slightly different form for definite integrals. But if I'm integrating v times du, so function v integrating with respect to u, I can rewrite that integral as v times u minus u times dv. So I take the antiderivative of one part, so i.e. the antiderivative of u or du, to turn it into u, and then re-switch this around so that then I can consider what u times the derivative of v is. All right, thank you for the heads up. So he's already gone, never mind. I'll just send him an email. So one of the nice things about this is that one of those parts, when I do integration by parts, I have to take the antiderivative of, but the other one I get to take the derivative of, right? Going from v to dv and then du to u. So I'm going to want to apply integration by parts here. Usually the term that I want to set to v is the term that I want to get rid of. And the term that I set du to is the term that I know the antiderivative of. Okay, and it's going to be pretty easy to compute the antiderivative of. So when I look at t times e to the negative 3t, I'm going to want to set v to be something, and I want du to be something. What do you suggest? There's only two scenarios, right?
Make e to the minus 2t v.
All right, that means du has got to be what? Well, t times the dt. The dt is what gets in there because it's part of the derivative. So then I take the derivative of e to negative 3t, and what is that going to be? What is the derivative of e to the negative 3t?
Same thing.
Not the same thing, close. Differs slightly. Just for the sake of time. It's negative 3 times e to the negative 3t. Because of that chain rule, I got to multiply by the derivative of what's up in the exponent. And then I keep track of the fact that I took the derivative with respect to time. That's where that dt comes into play. And then I go say, okay, what's the antiderivative of u? Or sorry, not u, of t with respect to time? Well, it's t squared over 2. So integration by parts then tells me that the antiderivative of t times e to the negative 3t dt is equal to u times v. So t squared over 2 times e to the negative 3t minus the antiderivative of t squared over 2 times negative 3 e to the negative 3t dt. So then I get another integral that's there. So now I have a t squared over 2 times 3, -3 times e to the -3t. Now, does that integral look like it's gotten a little bit easier to solve? What do you think? Or how do you feel? Yes or no? We started with integral being t times e to the -3t, and now we have an integral of t squared divided by 2 times a -3 times an e to the -3t.
Yeah, it looks harder to me.
Yeah, it's actually, it has gotten a little bit harder, but that's fine because we just made a choice of what v and what du was. And this didn't seem to work out. So what do I get to go back and do?
Change v and du.
Yeah, just change v and du, make a different choice and see if that helps me out at all. So no harm, no foul. Great thing about things with erasers, you get to erase it. And we get to try again. So instead, let's let v be the variable t. Well, what is the derivative of t with respect to time or with respect to t?
1.
Yeah. It's just going to be 1. So it's going to be a 1 times a dt, just to essentially record that I took the derivative with respect to time. And then, I don't know why that's there, I set du to be equal to that e to the -3t dt. In this case, its antiderivative is going to be itself divided by a -3. Because if I take the derivative of what I now see as u, I'm going to be multiplying by -3, then those two -3s will cancel each other out, leaving me with just that e to the -3t. So now I have a new way to rewrite this integral. So coming, just kind of centering all of this work a little bit, I'm going to rewrite it. E to the -3t times y is the antiderivative of t times e to the -3t dt. And now we're going to apply integration by parts. So it becomes my v times my u, which is going to be -1/3 t times e to the -3t. That division by -3, I'm just choosing to rewrite as a multiplication by -1/3. So that's my v times my u, and I'm going to be subtracting the antiderivative of u dv. So -1/3 e to the -3 times t. Well, dv was just dt. Let's try to write it below. uv u dv. Well, hey, the integral on the right-hand side's actually gotten a little bit easier now. Just doing some rewriting. I get e to -3t times y is equal to -1/3 t e to the -3t, nothing there. But one of my integration rules is I can pull out constant multiples. So I can pull out that -1/3. So I'd be subtracting a -1/3 times blah. What happens with those two negatives?
Cancel out.
And they cancel each other out, giving me a positive 1/3 times the antiderivative of 3, or e to the -3t dt. And wait a second, haven't we already done that? What's its antiderivative?
E to the -3t over -3.
Yep. And then plus some integrating constant c. And now look, do we have any more integrals to deal with? No. Do we have any more derivatives there? No. We got some stuff we need to clean up, absolutely. But now I just have my variable y and a bunch of other stuff, and I can actually solve for that y, figure out what the solution is supposed to be. So let's clean up that stuff on the right-hand side of the equality real quick. So I'm just looking at this e to the negative 3t times y. It's equal to negative 1/3 t times e to the negative 3t. But now if I distribute that 1/3 through, I take a positive 1/3, multiply it by a negative 1/3. That negative 1/3 is coming from the division by the negative 3. It's going to give me a negative 1/9 times e to the negative 3t. And then I get this constant c. If I take a constant and multiply it by a 1/3, it's still just a constant. You get to play that nice little constant game. It's a black hole. You multiply or divide it by any other constant, it still just becomes a constant. And I can still represent it with just some letter c. Now I want to solve for y. What is the last step I need to do?
Divide everything by e to the negative 3t.
Yeah, so you can divide by everything with an e to the negative 3t. Which is the same thing as multiplying as 1 over e to the negative 3t, but I can use a nice little, this is just to simplify it down. There's absolutely nothing wrong with that idea. But taking that, and this is just going to be a trick that makes things a little bit easier later on. Let me write it so it's a little bit more visible. There we go. How can I rewrite that, getting rid of that negative exponent? 1 divided by e to the negative 3t is the same thing as what? It's a nice little algebra rule. Oh, sorry. I keep interrupting y'all. Like, I think I wait long enough. I think I wait long enough for y'all to unmute, and then I start talking and I immediately interrupt someone. So I apologize for that. Just for the sake of time, it did sound like both of y'all said the right thing. It's just e to 3t. So I could, in one sense, think of dividing everything by e to the negative 3t, or I could just multiply everything by e to the 3t. Either way, they're going to come out, it's always going to cancel out with anywhere I see an e to the negative 3t. Giving me negative 1/3 t minus 1 over 9 plus c times e to the 3t. And this right here, oops, is my solution. The function that satisfies that differential equation is negative 1/3 t minus 1/9 plus some constant times e to the 3t. How can I confirm that this is the actual solution and that I did not make a mistake at some point along the way? Because there was a few calculus tricks that we had to pull back from the back of our mind, dust it off, and then use. Well, it's supposed to satisfy that differential equation. That is that dy over dt minus 3 times y is equal to t. So how can I confirm that that's the case? this function y is supposed to be the function such that when I take its derivative and subtract 3 times the function, it is supposed to just be t. So how can I confirm that this is the solution? See someone can chat. Nabari, quizzes are always at the beginning of class. So there's that. That's not with this question though. So answer is just like with algebra, plug it in. Plug your solution in, right? Figure out what the derivative of your solution is, which is the derivative with respect to time of -1/3 t minus 1/9 plus c times e to -3t. Figure out what 3 times my solution is, just 3 times -1/3 t minus 1/9 plus c times e to the 3t, which becomes -t minus 1/3 plus 3 times c e to the 3t. I don't know why I put a negative there. And I take the derivative. Negative derivative of -1/3 t is just -1/3. I take the derivative of 1/9, which is a constant, which is 1 or 0. Then I'm going to add, well, the derivative of e to the -3t, which is -3 times whatever that constant is, e to the -3t. So dy over dt minus 3 times y is equal to -1/3 minus 3 times a constant c e to the -3t minus 3 times y, which was that, minus t minus 1/3 plus 3. Whoops, why did that get a negative? That shouldn't get a negative. I'm just rushing because I know the time and I know y'all want to get out of here. But the point is, you plug it in, I distribute that negative through, so I have -1/3 plus 3 times c e to the 3t plus t plus 1/3 minus 3 times c e to the 3t. Everything cancels out, and I'm left with just t. So it's that old little trick when you're taking your algebra courses that your teachers probably always told you to do that you rarely ever did. Or if you're at least like me, rarely ever did. You'd find your solution to an algebraic equation and they would always say, plug it in just to double check. Right. And I never would, at least, or I rarely would, I should say, because I was pretty confident with myself that I was never making any algebraic mistakes along the way. However, with differential equations, it's much easier to make mistakes, right? So with these, when we're finding these solutions, it's always a good thing to just try to plug them back into the differential equations, see if they do satisfy. All right, I talked over much more than I thought I would. I do apologize for that, but while you finish writing this up, if you're wanting to, feel free to stick around and do that. If you have any questions, I know Shivana wanted to talk to me as well, so we'll stick around for a little bit and talk, ask questions. Otherwise, when you feel like you got everything, and if you got no questions for me, just shoot me a thumbs up and feel free to get on out of here. Let's see if I can rewrite some of this. So any questions for me? Or is everyone just writing this down still?
I just try finish copying the working.
Gotcha, gotcha. Whoops, sorry. I don't know, okay. My screen accidentally rotated. I didn't mean for that to happen. Keyboard.
Have a good day.
Thank you, you too. All right, let me stop the recording.